This video is on water disinfection and bleaching. This is a very important context that shows up regularly in the WACE exam. So we're going to start with talking a little bit about water purification. So the Australian Drinking Water Guidelines state that drinking water should be safe to drink for people in most stages of normal life, including children over 6 months of age and the very old. It should contain no harmful concentrations of chemicals or pathogens, and ideally it should be aesthetically pleasing in appearance, taste and odour. So appearance should be colourless, taste should be tasteless, and odour should be odourless. And that drinking water is water. That based on the current knowledge, it is safe to drink over a lifetime and that it constitutes no significant risk to health. If the water meets these criteria, it's considered to be potable water. So potable water is drinking water. Water purification for ground and dam water has a series of steps. The first is settling, and this removes colloidal material. So it will basically allow the water to become colourless. Then we have filtration, and this removes bacteria. We have aeration to remove excess carbon dioxide and hydrogen sulfide and increase oxygen gas. Disinfection is to completely remove pathogens. And fluoridation is for teeth protection. Now, in dam and deep groundwater, the first three are done naturally, and we just disinfect and fluoridate. In shallow groundwater, you need to do all 5 steps. The other main water source for Perth is desalinated water. It's Perth's biggest water source and provides 48% of all water for human consumption. Now, the processes for desalination is that it first of all undergoes reverse osmosis. So the seawater is forced through a membrane. And this removes salt, bacteria, viruses, and other impurities. The second step for treatment is lime treatment. Now, lime is calcium oxide or calcium hydroxide, and this is a remineralization process. And basically what we're doing is we're increasing the pH and alkalinity of the water. Then once again we undergo disinfection, which is to make sure it removes all pathogens, and then fluoridation to protect teeth. Disinfection by chlorination is probably the single biggest improvement for health over the past 200 years. So chlorination of our drinking water is the biggest contributor to our health, and without it we would all be drinking bottled water like we do when we go overseas. So community water supplies and community swimming pools, so we're talking about the big swimming pool centres, are treated with chlorine compounds that act as oxidising agents to potentially kill harmful bacteria and algal growths. The first example of disinfection we're going to be looking at is chlorination using chlorine gas. And this is only done for our community water supplies, so our dams, our groundwater, our desalinated water, and our public swimming pools. So the big public centres like Bayswater Waves, Inglewood, Terry Tyzack swimming pools, the big water supplies. So chlorine here is a poisonous gas. It is a yellow-green colour, and it has a pungent odour. Now it's also moderately soluble in water. And will form an equilibrium when it's dissolved in water. How do we know it forms an equilibrium? Look at the arrow. So when the chlorine dissolves in water, it forms hydrogen ion, chloride ions, and hypochlorous acid. And the hypochlorous acid is a strong oxidizing agent. And it's an effective bactericide and algicide. This is our principal agent for disinfection. So the hypochlorous acid, as I said, is a strong oxidizing agent. You need to be able to find it on your data sheet. And you can see here, it's right near the top. So it's 1 E0 for reduction is positive 1.49 volts. So it's a very, very strong oxidizing agent. So what happens is when you put chlorine into your water, it forms the hypochlorous acid. The hypochlorous acid can undergo reduction, and when it encounters any bacteria, what it does is it pulls an electron off its membrane, and this results in dead bacteria plus an electron. Now, unfortunately, chlorine, because it's so dangerous, is actually not very safe for the public to handle. So if you've got your own swimming pool, then you would be using either sodium hypochlorite or calcium hypochlorite as your disinfection agent. So liquid pool chlorine is actually sodium hypochlorite, and dry chlorine, the granulated stuff, is calcium hypochlorite. Now you may notice that the hypochlorite ion is sometimes written different ways, so be aware that both are okay. So what happens to make the sodium hypochlorite and the calcium hypochlorite is that you basically add sodium hydroxide or calcium hydroxide pellets to chlorine, and that makes the salt. And here's the equation. Sodium hydroxide plus chlorine gives sodium hypochlorite, and calcium hydroxide plus chlorine gives calcium hypochlorite. So these are the active agents. Now, these salts, when they dissolve in water, produce the hypochlorite ion, which is what we need for our disinfection. So the hypochlorite ion in turn will hydrolyze with water to form hypochlorous acid. So remember, this is our principal bactericide and algicide. So this is the most effective oxidizing agent. Even though this one is a good oxidizing agent, it's not as good as this one. Now, once again, you'll notice this is an equilibrium, and this equilibrium needs to be carefully controlled. So both the hypochlorite and the hypochlorous acid are really good oxidants, but remember, this is the one that we want. And we have basically controlled the amount of this one by manipulating the equilibrium position. So this equilibrium system is extremely pH dependent, and you can see this in the graph. So what's happening here in this graph is you can see that when you have a low pH, which means you have a high hydrogen ion concentration, remember this is an acid and this is a base, the hydrogen ions collide with the hypochlorite ions, and form the hypochlorous acid. Now this makes it really great for disinfection, but unfortunately at this point here you'll get sore skin and irritated eyes. So we've all swam in a swimming pool where you get sore eyes and things. So that's no good. Now, great for disinfection, but not so good for swimming. When you have a high pH, that means a high hydroxide ion concentration. You can see that the hydroxides would collide with the hypochlorous acid and produce the chlorate ion, hypochlorite ion plus water. This increases the concentration of the hypochlorite ion, which you can see happening in the graph, and unfortunately this is not as good at disinfection. So it's not as good at being able to disinfect your swimming pool. So we need to maintain our pH between usually about 7.2 to 7.8. So slightly basic region. So pH control of the swimming pool is extremely important, and you would be regularly testing it if you have a home swimming pool. And we maintain our pH in the swimming pool in that region between 7.2 to 7.8 by using a sodium hydrogen carbonate buffer, and there's the reaction for the buffer. So you can see why this is an important context, because it incorporates acid-base chemistry in the form of buffers, redox chemistry, and equilibrium. Now, the other use that we have for chlorine and chlorine-based compounds is bleaching. And bleaching is the process of converting coloured dyes to colourless products, and this occurs slowly in the atmosphere. So all of your clothes are slowly being bleached if you leave them on the outside line. Now, it's achieved more rapidly by using chlorine or hypochlorites, and it's used extensively in the textile and paper manufacture industry. So bleaching with chlorine or hypochlorites, the most is enhanced by using hypochlorous acid. Remember, it's located on your data sheet just here, and it's a very strong oxidizing agent. Bleaches can be solutions of hypochlorites such as sodium or calcium hypochlorite or chlorine solution, but they have to produce hypochlorous acid, which is the best bleaching agent. What we have here is a picture of a textile industry where they're bleaching different types of cotton. So what we have is your unbleached cotton comes in at this point here. It basically is treated with sodium hydroxide and sodium hypochlorite. Then it's washed with dilute sulfuric acid water, and then towards the end you treat it with sodium thiosulfate, and that's to remove any chlorine products still left behind, and then washed, and here we have our bleached. So the hypochlorous acid bleaches the fabric by oxidation, and the bleached fabric is washed and then treated with a mild reducing agent such as sodium thiosulfate to remove any residual chlorine. So this is how they remove residual chlorine. And then it's washed to remove any final chemicals. So this is a really, really important context because it incorporates equilibrium, redox, and acid-base chemistry. This context turns up on a regular basis, so I suggest that you make sure you learn this context very well and have a go at a comprehension from the OneNote. Good luck.